In this video, I will introduce simulation and measurement with a high accuracy of a rocking curve for crystal thickness. You may download Landyne SMART at the Landyne's website. Here is the icon of the Landyne SMART. Double click gives you the Landyne launcher. The Smart is here. Double click the Smart icon, give it the GUI. Here is the graphic panel and two main dialog, simulation and measurement. One of the application of the Smart is used to simulate the two-beam CBED pattern. The other application of Smart is to use to measure the crystal thickness. We will first go through the drop-down menu. The graphic menu can be turned on or off, on which listed the selected items from the drop-down menu. And the crystal, first one is the new data. Provide a template for prepare a new crystal data. Next is load the crystal. Select the crystal structure in the structure data collection. This is the quit the program. And the experiment. The experiment pattern can be loaded from a file system or the drag and drop function. Bring the image to this box. Next is the inverse the contrast of the image. Erase the loading image. Here are caliber for measure the scale bar or the G factor of the diffraction pattern. This is the same as measurement dialog box. We'll go through it in detail later. The last one is the drawing panel and the result table. We'll use it later. And the calculation, first one is max scope. We'll set up the HT of the max scope. Next one is to calculate the diffraction disk and calculation the extinction distance. Set up the diffraction vector for two beam case and calculate the extinction distance. Next is the set up the absorption coefficients, and this is the same as the simulation dialog. We'll go through this in detail later. Last one is for erase the simulation disk and curve. And the output will set up range interest, and we can add a figure number, and we can save the display within the range of interest to file in format of TIFF, PNG, JPEG, GIF. Under the table, you can show the periodic table of the elements, you can show the base group standard setting, and also graphic non-standard setting. Under the option, as we mentioned before, you can show the graphic menu bar or hide it. You can change the appearance with a different style. You can change the size of. And the help, first one, the dialog show you current drive serial number. You need to submit the serial number for a license, and this is the version information. Let me show you the data template. It allows the standard setting of the space group, or you can use the earlier alternative space group setting and make the transfer. First, select the space group number and select the origin if there are two origins in that space group. The space group will make the lattice parameter simplified. If it's cubic, only A is available. Then add atoms. You can add or remove or make a change of that. You can view how many atoms you put in, and you can save the structure data to a file. You can renew the whole interface, or you can transfer the standard CIF file directly to the format used in the Landyne SMART. To simulate a two-beam CBED pattern, first you need to load a crystal structure from the data collection, or use the default. The default one is the aluminum. And then set up the wavelengths. You can put the microscope high tension here and do the calculation. And define the extinction distance. This two value can be done by do the HKL here, calculate the reciprocal length and extinction distance, and do the transfer. You can change the sample thickness anytime, and then suppose we use the value of the default here, you can change the color of the curve. You can show the curve or show the pattern here. And the following is the appearance of the simulation result. This is to set up the curve baseline position, and this is show the curve's height. This shows the pattern's position. It shows the diffraction position. Last one is show the radius of the diffraction is related to the size of the aperture. That's how you making a simulation of the two-beam CBED diffraction. The SMART system have a full option to display the curve and the diffraction disk. This is just one diffraction pattern here, one different curve. If both of them I'll show you like this. The experimental diffraction disk or curve will use the same place. So before load the experimental result, you have to hide either one or both of the simulation patterns. To measure the crystal thickness by use the two-beam CBED pattern, first we need to load the experimental diffraction pattern. Use file system. There it is. Or use drag and drop way. First, let's erase this pattern. You can, for example, just drag and drop. Next, we need to upgrade the scale information here. If you know the crystal structure, you can use either scale bar or the G factor. If you don't know the structures, you have to use the scale bars. We provide for scale calibrations, so you can use mouse move here. If you have a scale bar here and you matched with the scale bar and you feel the real value here, then it's that. If you don't have the scale bar here but you know the structures, revise the contrast, and or you can measure it from here and drag this. And then you refill the G vector here to do the calibrations. Once this done, you can search for the old disk by drag this point in the center of the disk, and use the mouse wheel, change the reddish, recorrect the center, and find exactly the disk. And now find the G disk. But remember, you had to select the G disk first, then find the center, move. Once you find the two disks, then you can transfer. So you got remember that's only two places. This is the curves from the experimental patterns. We have these two places either show simulated patterns or experimental curve and patterns. You can mix them, but only two of these patterns can be shown here. Once you got these curves, you can find out defined where the center points. And this gives you a guide here. So you can move this one, help with the curve and the brightness. So this will be the blurry condition. The G vector very close to 0.5 compared to the calculation is 0.4941. And then we make a minimum position. You can see from here to the first one, second one, third one, the fourth one. We can add one more. Then do the calculation. This line is supposed in one line, so means that the calculation one didn't work. So we try to increase to number 2. It's still not in this line, so we had to increase to number 3. Here they appeared in one line. Let's check the extinction distance is 1000, but we know that for aluminum 200 the extinction is 846, so even the 3 is close to on the line, but still not good. So we try number 4 here. So now everything is online. We check that the extinction is 849. It's very close to the applied one, 846. So the calculation should be, for the thickness should be close to, we set up 3000 and the measurement is 2959. So it's quite close to we set up. This is how you use the 2-beam conversion beam to measure the sample thickness. If the thickness is really thin, you don't have so many minimum local, and this way calculation may not work. If you know the structure, you can make a simulation and compare to the experimental result. In that way you may estimate the real thickness of your samples. So this will be the only curves from experiment. And now we make a calculation. We know this is aluminum. This is the calculation. You can adjust here the thickness and get simulation curves and try to match experimental curves. If you find a similar one, and your estimate for the thickness. In this video we show some basic use of the SMART software. It is suggested that you already know the theory and then use the SMART. Thank you for your watching. Please check other videos in the Landyne suite.